This will be available. This meeting will be available. We'll send a link out to everybody who signed up for this meeting. So our speaker tonight, we welcome back Dr. Andy Marvin. Andy is a professor, I can't even speak, is a professor emeritus at the University of York and a Leverhulme Foundation Emeritus Fellow. He was the founding technical director of York EMC Services Limited, now Eurofins York, and until December 2017, the professor of applied electromagnetics in the University of York's Department of Electrical and Electronic Engineering. He received his BE, ME, and PhD degrees in electrical and electronics engineering from the University of Sheffield between 1972 and 1978. From 1977 to 79, he was with the British Aircraft Corporation at Filton, Bristol, UK, working on antenna design and EMC. Andy was appointed to a lectureship in electronics at the University of York in the UK in 1979, promoted to professor of applied electromagnetics in 1995. And in the interest of time, I'm going to cut that short and give the time over to Andy Marvin so he can begin his presentation. Welcome, Andy.
Well, thank you very much, Scott. It's good to see people again. I mean, I think you may remember I was with you back in October 19.
Yes, I do, very much.
Yeah, I'm feeling rather better now. I had a dreadful cold that entire week I was in the States.
Oh, gee.
I felt absolutely ghastly for most of the time. But anyway, I did enjoy myself, and I did enjoy seeing a lot of people and seeing a lot of places. But so what I'm going to talk about today is slightly different to what I talked about a couple of years ago, 3 years ago nearly. There, I think I was talking about shielding in the round. I want to talk today about shielding of board level shields, a much smaller sort of artifact, if you like. So I'm going to start sharing my screen now. And let's get that up there. There we go. So hopefully you can see that. Can everybody see that? Is that coming through?
It's coming through great.
Okay, that's good. So circuit board shielding effectiveness issues and measurements. And along with myself, I've got my co-worker, Dr. John Dawson, who I've been working with on this for a number of years now. And so John, I've worked with, well, actually, John was one of my undergraduate students back in 1979. He doesn't seem to have gone away anywhere, so we still work together. And also his wife, Dr. Linda Dawson, works with me. So I hot desk with Linda now, in fact, as an emeritus chap rather than a guy in full post. Anyway, let's get on with things then. So circuit board shielding effectiveness, issues and measurements. The first thing that happens, of course, is that the thing refuses to move forward. Let me just sort of stop the share for a moment and go back in and see if I can just get that to. Hang on. So why? Let me just put that down for a second. Okay, so my system is locked up. Just give me a moment or two to try and unlock my system.
No problem.
Okay. Right, okay. Let's get back in there and share the screen again. Right, okay, so we're working on some different buttons, if you like. Okay, so board level shields then. Well, they're EMC components. And you can see that in the picture there, they come in the sort of the usual sort of plastic strips that enable you to look at them as components. Now, we've been working on a project which is the IEEE Project 2716, which is concerned with board level shielding. And the part of that project states that methods currently described in IEEE 299 and 299.1 for standalone shielded enclosures are not really applicable to board level shielding because of the various peculiarities of board level shields. And a board level shield, as you can see, is a component. It's not a standalone enclosure like a normal sort of shielded enclosure. It really only has 5 walls. The 6th wall is the ground plane of the circuit card that you mount the shield on. And so the user of the board level shield is in part responsible for the performance that you get from the shield. Now, board level shields are much smaller than the normal shields. Typical dimensions for a board level shield is something around 100 millimeters or less. And that'll be the largest dimension. You can see a picture down there on the left of a board level shield on a circuit card with a scale nearby. And you can see that one's about 50 millimeters in its largest dimension. And if you look at the the orthogonal dimension to that, it's probably about 30 to 40 millimeters and maybe 4 millimeters high. So it's quite a small device and it's a small compact device. So the size of the shield makes installation of internal measurement antennas, the sort of thing that you get in the shielding effectiveness standards, totally impractical. And that means that we basically can't use them. The other thing on the slide there says there only functions to act as a shield. Now, that might sound a bit strange, but if you look at something like a shielded enclosure you might have for your tower computer, for instance, or the fuselage of an aircraft, these things have a shielding function. Obviously, that's a secondary function in terms of the aircraft fuselage. The tower computer, it may well be one of the principal functions, but there are other functions as well. And if you take the tower computer case as an example, then there are there's a safety element to it. There's an appearance element, all sorts of things, as well as it being a shielded enclosure. Board level shields are only there to act as a shield. You don't see them typically. Now, because you don't see them, that means they're inside something. And they're installed in various environments. They may be in an outer equipment enclosure, which in itself is shielded. It could be resonant or it could be reverberant. Or they may be in an unshielded enclosure, such as the router, which you can see in this picture here. This is a circuit card from a router. And you can tell it's a router because you can see all the various antennas on it. That router card that I took apart was one that my internet provider sent as a duplicate by mistake and wasn't terribly interested in receiving back. So I sort of pulled it apart to see what was inside. And hey, there's a load of board level shields in there that make it good for demonstrations and so on. If the board level shield is enclosed within an ordinary equipment enclosure, a much bigger equipment enclosure, I mentioned that it can be either resonant or reverberant. Let's just sort of run through what that might mean for a moment. You're probably aware that any enclosure will be subject to resonances as we go up in frequency. And typically those resonances are, for most normal size enclosures with dimensions of around a meter or less, those resonances kick in at a few hundred megahertz, and they come along according to the Helmholtz equation, modified by whatever's in there in the enclosure, at irregular frequency intervals. But those irregular intervals get more and more close together as we go up in frequency. As we get up into the microwave frequency range, which is where my colleague and I are particularly interested, then those resonant frequencies come thick and fast, and the gaps between them get very, very small indeed. They go from perhaps a few hundred megahertz between resonances to a few megahertz, and then down possibly to less than a megahertz between individual resonant frequencies. And when we get to that regime, where we're getting lots and lots of resonant frequencies, then we're in the reverberation regime. And that's where the resonances are overlapping. Because if you think of any resonance, it has a Q factor. There are losses associated with the resonance. And so the resonance has a bandwidth. And if you're getting resonances very, very close together, then that bandwidths will overlap. Typically at any particular frequency, several resonances or even many resonances will be excited. And then the field structures inside the enclosure change from the sort of geometric structures you find for resonant into, well, basically we're talking about reverberation chambers and motor chambers and all the wonders and complexities associated with that. So we may find ourselves in that regime, or we may find ourselves in a rather more non-resonant regime, but perhaps with other antennas around us. So all we can say when we're thinking about what we might do with a board level shield in terms of how to assess it, and there are no methods at the moment of assessment that are recognized sort of by standards bodies as far as we know, then all we can say is basically that we are dealing with what you might call known unknowns. We know what the unknowns are, but we don't know what the answers are at the moment. This is what we've been looking at. So let's think about the sort of the application and the internal environment. I mean, the board level shield is there to shield something. And the internal components may act as interference sources, or they may suffer from external interference. So it's just like any other EMC problem. We might be dealing with emissions, or we might be dealing with immunity. And any contents inside the enclosure, inside the board level shield, will absorb some of the electromagnetic energy that gets inside the shield. And so they need to be accounted for in any shielding measurement. Now, you might have heard me talk about this when I was talking about shields 3 years ago on much larger shielded enclosures. I've been sort of promoting the notion that for many years now, that when we talk about shielded enclosures, we should be accounting for what we put inside the shielded enclosure. We can't just talk about the enclosure in isolation, because nobody ever uses an enclosure in isolation. They use it to enclose something. And so here with board level shields, we've got stuff inside, and you can see from the picture there that there's a board level shield with its frame soldered to the circuit card and the shield cover taken off to expose a number of large-scale integrated circuits, transmission lines, resistors, all sorts of things inside that board level shield. Those things in there will absorb whatever electromagnetic energy is present inside the shield and modify what's going on. So it's not just the shield, it's what's inside as well. Now, if we look at the kind of coupling paths that we might have to deal with, let's think about that for a moment. Again, a picture on your left. There are direct coupling paths just going straight through the shield, or whatever apertures are in the shield. And so I've drawn a double-ended arrow there towards the top, which you can see here, if you can see my arrow. And that's the sort of, there's an integrated circuit inside the shield there. Here's an antenna on the edge of the router card. And so there may well be some direct coupling between the antenna and what's inside the shield. In addition to that, if we're inside an external enclosure potentially, then there may be an indirect coupling path scattered from the external environment. And so what we've got there is a potential for a very complex coupling between the external source of interference and the internal victim of interference, or vice versa, the internal source of interference and the external victim. We don't know which way around it's going to be, of course. But we're getting into sort of rather complicated situation. We really got to think in terms of how we can cope with this sort of situation that we find ourselves in with these shields. So we'll come on to sort of what we do about these different types of environment. The other thing that we have to recognize with board level shields is that there may well be provision for desired propagation of signals into and out of the shield. And you can see a couple in this application here of a board level shield. Very obvious transmission lines at the pointy end of the yellow arrows there. Transmission lines penetrating in and into or out of the shield. And so if we're going to try and assess the performance of that board level shield, then maybe we ought to think about excluding those signal paths, because they're there anyway. We don't want them to be there in terms of assessing the board level shield. So I'm building a sort of picture of some difficulty and some complexity. And it's quite challenging. to measure the SE of a board level shield. I mean, here's a almost extreme example of a board level shield. I say it's difficult because of the small size. You can see a board level shield there that is literally 10 millimeters in its largest dimension. And so that makes it quite challenging. And that variable local external environment, again, adds to the complexity. What we can say, though, is that most likely any victim or source of interference external to the shield is likely to be on the same circuit board. If that board level shield is being interfered with or causing interference, or something that's actually outside the device in which it's installed, then we've got a really major problem, and we shouldn't have a problem like that. I think we can say that for the most part, almost certainly, it's going to be a local source of interference or a local victim of interference that the shield is there to protect. So when we come to think in terms of what we're going to do to measure the effectiveness of board level shields, then we can think in terms of local sources and local sinks. So here's our prototype measurement jig that we've been doing in P2716. Now, the prototype measurement jig is, of course, built on a circuit card, printed circuit card. It's just a piece of FR4 circuit card. Obviously, it has two sides. It's metallized on both sides. On one side, we have some strip lines. Now, a little bit difficult to see. It's quite difficult to photograph these things. But if you look inside the this ellipse here, this yellow ellipse, you can see there is, in fact, a strip line mounted above the ground plane of the circuit card ground plane. And that strip line is terminated with SMA jacks at each end. I've called that the S, or the shield strip line. 25 millimeters long. Now, 50 millimeters down from there is an identical strip line, again terminated with SMA jacks, which is 25 millimeters long. And that's parallel to the shield strip line, so that gets called a parallel strip line. And then 50 millimeters over from the shield strip line, or the center of it, is an orthogonal, again identical 25 millimeter long strip line, again with 50 ohm terminations at each end. And those are 50 ohm transmission lines. So these strip lines are there to replicate in some way the external sources or sinks of interference on the same circuit card, and the strip line inside the shield is there to replicate the internal circuitry inside the shield. I mean, so this is a sort of representative contents, if you like, inside the shield. Remember from my talk about 3 years ago, talked about that. So these are our representative contents, and these are potential sources and victims of interference there. Now, if you look at the other photograph there, you can see on the right-hand side, you can see the opposite side of the circuit card, and you can see the three pairs of SMA jacks that are terminating those strip lines. And you'll notice that they're well soldered to the ground plane. Now, clearly, if we're going to be measuring the shielding effectiveness of any circuit card shield we're going to put on top of the shield strip line, we have to make sure that the energy penetrating into it only comes through the shield itself, through this board level shield itself. And so, taking a lot of trouble to isolate the internal strip line. And you can see that around the jacks on the internal strip line, there are some an array of in fact there are 6 plated through holes connecting the top ground plane to the opposite ground plane, the bottom ground plane on the other side of the circuit card. The hole through which the inner conductor of the SMA coaxial connector comes is also plated through. And so there's a good conducting connection between the top of the circuit card and the bottom of the circuit card to make sure that nothing that gets into the sort of the gap between the two metal layers on the circuit card can actually penetrate into the shield. So a lot of trouble taken to do that, and it seems to be effective. So that's the sort of the jig that we have. And you can see here that we're applying the frame of the soldered on board level shield. That's just been soldered on above the shield strip line there. And you can see that the parallel and orthogonal strip lines are outside the shield. And so this is very much a prototype jig that we've been working with. Dimensions are pretty arbitrary, really, but the dimensions fit the dimensions of just about every board level shield that we've come across. And then on the right-hand side picture, you can see the shell, the board level shield shell, clipped over the frame there. And it's just a press-on clipping connection. And this is one of the weaknesses of the board level shielding shields. That they are, because they're sort of components in this way, they're perhaps not as well made as a good shielded enclosure. The shell simply clips onto the frame, and you can see that the solder is at a number of positions along the periphery there. It's not a continuous soldering connection, and that's the way that, if you look at those pictures I showed you earlier, that's the way in which they're actually deployed. So what do we actually measure? Well, I've mentioned that we're working with an unknown external environment. And if you've heard me lecture before, you know I'm a fan of reverberation chambers and like to use reverberation chambers. So we make our measurements inside a reverberation chamber. And the nice thing about the reverberation chamber is that as you stir the chamber, we move the mechanical stir around, that gives us a very variable, unknown external environment, or it mimics the unknown external environment of the installed board level shield. So we stir the chamber and we're putting lots and lots and lots of different environments, different external environments on the board level shield. And you can see in the picture there, we've got two of the jigs. The one on the left has the shield installed, and the one on the right has no shield installed. And you can see that going from the prototype jigs, there's a couple of semi-rigid cables connecting the strip lines to the vector network analyzer, which is outside the chamber. And then we've got a couple of antenna cables as well. There's a couple of antennas inside the chamber as well for monitoring purposes. But basically what we do is we measure the coupling between, say, the parallel strip line and the shield strip line without the board level shield being present. So that would be measuring the coupling between these two strip lines on the empty jig and look at the power couple between them. And then we look at the power couple from this strip line into the shield, or vice versa. It's reciprocal. And then we've got a measure of the effect of that board level shield, which hopefully tells us something about it. So that's the basic measurement setup then. And then we have some definitions of what we're actually looking at. So our basic measurement is an S21 measurement between the shield strip line and an external strip line. Each strip line is terminated in a 50 ohm load at the other end. So we've got the network analyzer connected to one end of the shield strip of the strip lines and a 50 ohm load at the other. It says here the shield strip line mimics the internal components of the shield, and it absorbs energy within the shield because it's got a match load at each end. Unknown external environment mimicked by the stirring process in the reverberation chamber. Measurements made with and without the shield present. Okay, so we came up with a couple of definitions. And the first definition was our unstirred shielding effectiveness. And this is equivalent, if you like, to the direct coupling, say, between that antenna on the router card and the integrated circuit that you can see inside the board level shield. Obviously, I've taken the lid off the shield there, taken the shell off, just to sort of show what the coupling path is. And if we look at the equation there for the unstirred shielding effectiveness, it's expressed in decibel terms. But if you look at what's inside the log there, we've got S21 unstirred divided by S21 stirred. In other words, we're assuming that the unstirred S21, the unshielded, I beg your pardon, S21 unshielded divided by S21 shielded. We're assuming that the unshielded is going to give a bigger signal than the shielded. And so we get a positive shielding effectiveness in terms of decibel numbers. The internal brackets, the pointy brackets there, are the average. So these are averages of the S21s over the rotation of the stirrer, over the entire rotation of the stirrer. And that average basically gives us the unstirred component. It's a vector average or a phasor average. So it averages out to leave the unstirred component. So that's the direct coupling. And so we're looking at the unstirred shielding effectiveness there, the direct coupling. Now, we can also look at the stirred shielding effectiveness. And again, the stirred shielding effectiveness is where we're looking at the coupling that has come through scattering from the external environment. So it's not the direct coupling between the parallel and shield strip line. It's bounced off the walls, or it's done some other propagation path other than the simple direct path. And the way that we do that is to look at the unshielded and shielded S21s again and subtract from them the phasor average. So we subtract out the unstirred component and just leave us with the stirred component, the bit that's gone through the reverberation process or the resonance process within the enclosure there. And we remove the direct couple component, and so we get an idea of the stirred shielding effectiveness. And we thought about that, and we thought this was a pretty good measure, or these were two pretty good measures that tell us something about the effect of the board level shield. And we published a paper on that, or a couple of papers on that. And then we said, let's think about this a bit more. What actually happens here? What do we need to know? Well, we've got an unknown external environment. We don't know what's going on. What we really need to do is to say, what is the shielding effectiveness of that board level shield at every sample of our mimicked external environment? And then we can say how the external environment will actually affect the shielding of the board level shield, the extent to which it will affect it. As we say, we don't know what the external environment is. We don't know where the shield is going to be deployed. We're manufacturing these things. We sell them on. We don't know how they're going to be used. We can't determine that. So if we look at all the external environments that the reverberation chamber allows us to mimic, one for each stirrer position, we can look at the shielding effectiveness of that board level shield at each of those positions. And we christen that the point shielding effectiveness. So that metric, the point shielding effectiveness, explores a range of variability of the external environment and the effect it has on the shielding effectiveness. And that reverberation chamber allows us to do that in a very effective way. So if we've got n stirrer positions, then the shielding effectiveness at position n is simply shown in the equation there. It's the ratio of the unstirred shielding effectiveness, position n, to the, the unstirred S21 at position n, to the shielded S21 at position n. I'm getting unstirred and stirred mixed up in my mind with unshielded and shielded. So let me start again. It's the ratio of the unshielded S21 at position n to the shielded S21 at position n. Square that up to make it power, and then you've got the 10 log. And there's your shielding effectiveness at position n. And then we can look at the statistics of that, and we can take the mean, for instance, and look at the mean point shielding effectiveness and standard deviations. We can look at the statistical distribution of shielding effectiveness in a variety of external environments. Now, my colleague John Dawson, who does a lot of the data processing in this. I do the measurements, he does the data processing. That's the division of labor between us generally. And he's sort of thinking about this, and he had a look at the cross correlation between the shielded measurements inside the made with the coupling in, with the shield present, and the unshielded measurements. And you can see the correlation there. On the the left-hand horizontal axis, if I can describe it as that, is the frequency. We're going from 200 megahertz up to 20 gigahertz. And then on the right-hand horizontal axis, if you will, is the offset between the stirrer positions for shielded and unshielded measurements. And our stirrer can do 6,400 positions, and so it goes to 3,200 on either side. And you can see on the vertical axis is the cross correlation between unshielded and shielded measurements, and there is none effectively. So what John then did was to say, okay, rather than just doing this point shielding effectiveness, we'll actually take it a stage further, and we'll ratio every measurement made without the shield present to every measurement made with the shield present. So when we use 100 stirrer positions, instead of having just 100 shielding effectiveness measurements, point shielding effectiveness measurements in our statistics, we've now got 10,000. We've got 100 times 100. And you can see the plot there of the shielding effectiveness density function. The one on the left is at 15 gigahertz for that particular shield, and shows a mean of 16.2 dBs with a standard deviation of 6.2 dBs. And the SE all with the 10,000 points, as you can see, overlays the SE point. And if you look at the fitted distributions there, it turns out to be in decibel terms a normal distribution. So it's a log normal distribution. They're pretty identical. And again, looking on the right-hand side, we're doing it at 4 gigahertz, where the shield is rather better. It's now a mean of 39 decibels, shielding with a standard deviation a little bit smaller, 5.8. So you can see at those two different frequencies, we've got very different shielding performance. But the distributions for both the point SE and what we call SE all the points 10,000, are virtually identical. So that's what we decided, or that's where we got to. That's where we thought that was a good sort of measure. And we can plot them now over the frequency range from a couple of hundred megs, which is the lowest frequency which our reverberation chamber works, up to 20 gigahertz there. And you can see we've got the point average, it's the SE all average inside on the middle trace there, along with the plus minus 3 standard deviations on the outside, which gives you virtually all the variation that you're going to see. I think 3 standard deviations give you about 98% of samples. And you can see shield number 4 in our P2716 experiments. Doesn't really mean very much. And that's with coupling to the parallel strip line. And then the other one on the right-hand side is shield number 1, coupling to the orthogonal strip line. And again, you can see the plus minus 3 standard deviations and the point average SE inside the line there. So they fit very nicely inside the line. So does it match with reality? Well, we had a look at this as well. So what we did to see whether this fits with reality, if you will, was we had a look at simulating some real enclosures. Now, what we've got here is a small enclosure, a small metal enclosure. In UK terms, it's called a die-cast box. It's made out of some cheap aluminium, and you get a screw-on lid, and they're quite cheap, and you can make some electronic devices inside them. They're quite nice things. I guess you must have something similar in the US. This is a 50 by 110 by 180 millimeter box, so it replicates a small equipment enclosure. And you can see, if you look at the right-hand picture there, that we've, to complete the enclosure, we've simply screwed that box onto the top of our prototype measurement jig. So our board level shield is inside that equipment enclosure now, that simulated equipment enclosure. The equipment enclosure, as you can see, has a number of apertures milled into it. This is repurposed from another project. So those apertures were there, and they replicate the apertures you might find in a real equipment enclosure for ventilation or display or whatever. And then there's a bit of LS22 carbon-loaded polyurethane foam, just to add a bit more energy absorption as well, to make it look like a real enclosure with some other contents. And a couple of little SMA jacks there with extended inner connectors, which are very useful probe antennas. And they were used for measuring the Q factor of this this enclosure when we did the measurements, the experiments. So we measured the shielding effectiveness of the equipment enclosure there, of the board level shield rather, inside that enclosure. Now we also had a second enclosure as well. This is a much larger one. This has dimensions of 170 by 400 by 460 millimeters, and we mount the jig inside it there. And you can see that's an enclosure with quite a lot of ventilation holes in it. It's just a commercial enclosure that we have for other purposes. The prototype jig's mounted inside it, and then there's a little sort of probe antenna just here that assists us with Q factor measurement. So that's the large enclosure. So let's see what sort of results we get then. So this is the mean shielding effectiveness of the board level shield in the reverberation chamber with plus minus the 3 standard deviations. That's the shield that we used inside these enclosures. It's virtually identical actually to the unstirred shielding effectiveness I mentioned earlier on. So that's the measured SE of the board level shield. Now this is the measured SE data in the large equipment enclosure, and you can see it's quite variable. And the pale blue curve there is the actual measured SE inside that equipment enclosure. And then if we run a 50-point moving average over it, that's the dark curve that you can see overlaying the pale blue curve there. And if we look at that darker curve and overlay it on the right-hand diagram with the SE, the SE all, or the point SE that we measure inside the reverberation chamber, you can see that they overlay pretty well. And the sort of the underlying shielding effectiveness of the board level shield is quite apparent there. So when we put it inside the large enclosure, we get that underlying shielding effectiveness of the board level shield modified by the external environment of the larger enclosure. And you can see the modification there in the pale blue data. So that was with the large enclosure. If we look at the moving average data for the large enclosure and then the smaller enclosure, both with 7 apertures and the LS22 in it, and the LS22 removed and the apertures closed over, sticky copper tape does the aperture closing for you. Normally I have a graduate student use that because you cut your fingers to pieces on it, but in these cases I had to do it myself. That's part of the deal for being retired. Again, you can see that the large enclosure and the small enclosure in 2 configurations, low Q and high Q, shows that with the moving average, the underlying shielding effectiveness of the board level shield is there. It's still apparent. Let's have a look at what happens with the smaller enclosure with no apertures. So that's the high Q configuration, and we looked at the small enclosure, measured its Q factor at 15 gigahertz, and it's a Q factor of about 1,400. And we look at the measured shielding effectiveness of the board level shield inside that enclosure and overlay it with the plus minus 3 standard deviation data taken from the SE all measurement in the reverberation chamber. And you can see that the actual shielding effectiveness exhibited by the board level shield in the replica enclosure sits pretty much entirely inside the 3 standard deviations from the reverberation chamber measurements. So that gives us some sort of credibility, if you will, that the idea of measuring the board level shield in this point SE or this SE all way and looking at the statistics tells us something about how the shield will behave in this case, just one particular external environment. But it does seem to show that it gets the variability. We can do it again. This is the small enclosure with 7 apertures and absorber inside, so that's a low Q effect, a Q of 250 now at 15 gigahertz rather than 1400. And again, you can see the measured SE, much less frequency variation, but it still sits inside the 3 standard deviations measured inside the reverberation chamber. So again, we say this is evidence that this is a potentially useful measurement situation. And again, this is the large enclosure. Q factor is 4,700 at 15 gigahertz. And again, the data for the shielding effectiveness measured inside the large enclosure sits nicely inside the 3 standard deviation measured in the reverberation chamber. And what we've got then is a potential measurement environment that we can use. Now, that's fine. We've got what we think is a viable measurement system that we can perhaps present to a standards organization to see if they like it and something that we might be able to work with. But one of the things that we learned when we were doing this work was that attaching board level shields to the jig is both time consuming and it spoils the board level shield. You can see a picture there of the board level shield connected to the jig there. And you can see my rather rough soldering there. But at each connection point, I've soldered it down onto the ground plane. Now, that takes time, and you want to remove the board level shield from the jig as well. And believe you me, unsoldering the board level shield takes a lot longer than soldering it on there. Getting all that solder off and then getting the thing off takes a long time. And we found that with a lot of these board level shields, they're actually quite fragile. You tend to damage them. You know, best will in the world, it's very difficult to take a board level shield off a printed circuit card. So is there a simpler way? Also taking them off with solder, I mean, you have to clean up the jig as well. So is there a simpler way? Well, our first look at this was to say, well, can we just clean up the surface of the jig, clean up the surface of the board level shield, the attachment points, and just press the board level shield onto the ground plane of the jig and use simple spring pressure to do that. Now, we made a jig. You can see it on the right-hand side there. What it is, you can see at the bottom there on the circuit card, the board level shield is being pressed down. There's a block of expanded polystyrene sitting on top of the board level shield there. That serves 2 purposes. One is it gives a little bit of cushioning and makes sure that we get a nice even pressure all the way around. And the other thing it does is it gives some gap between the board level shield and the metallic springs, which are about 50 millimeters above it, which gives us a distance of a quarter wavelength at 1.5 gigahertz. So we're trying to keep those 4 springs that you can see away from the shield itself. In the reverberation chamber, that spacing is perfectly adequate. And you can see what happens is that we screw down the top perspex plate to compress the springs, and that force is transmitted through the bottom plate and the expanded polystyrene onto the board level shield. Now, each spring has a spring constant of, it says 0.49 newtons per millimeter. So we get about 2 newtons per millimeter contact pressure, which is 0.2 of a kilogram, 200 grams per millimeter contact pressure approximately. That's assuming that little g is not 9.81, but meters per second squared, but 10 meters per second squared. Anyway, there you go. So typically we press down the spring jig there and make some measurements. Now, nowhere could we find, not surprisingly, any data on the board level shields that said how much pressure you can put on the top of them. So we chose a couple of pressures, and the 2 pressures that we chose were a compression of 2 millimeters, which gives us a force of around 4 newtons, 0.4 of a kilogram. That's just under a pound in old money, or 5 millimeters, which gives us a kilogram. So that's just over 2 pounds pressure, if you like, on top of the board level shield there. And here's the results that we got. So looking at the graph on the left there, the light blue line at the top, around 60 dBs, is our measurement dynamic range for this shielding effectiveness measurement. This is the SE, or the point SE, or the SE all again. The middle graph there at around sort of 20 to 40 dBs is the actual shielding effectiveness, the SE all, or point, of the soldered board level shield. And the two graphs underneath are with 5 millimeters and 2 millimeters compression. And you can see that we're not getting any comparability with the soldered connection at all. So it didn't take long to sort of figure out that this was not the best idea in the world. It didn't work, basically. And so having got slightly frustrated, I screwed the springs down as far as they would go, and it still made no difference. It didn't damage the board level shield either, but there you are. So is there anything else we can do? Well, the next thing we tried was to use silver conducting paint. Silver conducting paint is readily available from most electronic suppliers. It's easy to apply, as you will see when I show you a video in a moment. And in fact, you can see from the this bit of a video here, it's actually easy to apply all over the place. I've got it on just about everything in the end. It gives you a joint that is electrically quite good, but it's mechanically fragile. So to apply it, we used the spring jig with 2 millimeters compression, and we made the measurements with the silver coated paint applied to the spring jig, also with 2 millimeter compression. So we used the silver coated paint to give us our good electrical contact between the solder tags and the board, and the spring jig to sort of hold the thing on. And I'll show you sort of applying it here, if my video will play. I hope it will. You'll see my shaking hand in a moment. Here we go. And the first one doesn't work, so we come back again. And we get a nice little contact there. And believe me, this is much easier than soldering. I've got to knock it out of the way there. That one worked quite nicely. Only 40 seconds of video. There's a big lump going on there. That's a nice connection as well. And at this point, really, I should have given up and stopped the video, because you can see I get it everywhere. But, you know, a little bit of solvent will soon get rid of that. So there you can see that we can readily apply it. And to take the board level shield off the jig there, give it a flick with your finger and it's off. Oops, hang on. Come on again. There we go. So here's a picture of a different shield connected to the jig with the silver coated paint applied around the connection points. And you can see that it gives, it looks like a solder joint. It sets in a few minutes. 10 minutes is the specification. And so you can start making measurements very quickly. And it's very easy to get the jig, or to get the board level shield on and off the jig. You can clean it up with solvent, and you can make some quite good measurements there. So let's have a look at some data from this. Well, before I do that, just note that this particular board level shield, you can see here and around the edges here, the structure of that particular shield is a little bit crude, really. You can see it's got some apertures in it as well for ventilation, but it's so easy when applying this jig to get that gap, to move that gap. That face of the board level shield there very easily moves relative to that face. And so these things are quite, in many ways, quite crude. But that's the sort of thing that we're working with. So here you can see on this graph the results of the silver coated paint with 2 millimeters compression on the clamp compared to the soldered jig, and they're virtually identical. So that gives us some confidence that we're actually making quite a good connection here. We've got a pretty good comparability between the soldered connection and the silver coated paint. Now, the silver coated paint has a curing time of 10 minutes. So the results here are 3 results. One 15 minutes, or one with the measurement done 15 minutes after the cure, so 10 minutes curing time, and then pick the whole thing up, take it into the chamber and start the measurement going. And then 2 hours later, basically that means after lunch. So the first one was done before lunch. I didn't have a 2-hour lunch break, but well, I did actually probably on that day. I am retired. So 2 hours after lunch, 2 hours later, no significant change. And typically these days I work a 1-day week. I go in on Tuesdays most weeks. But having done those two, the 15-minute and the 2-hour measurement on the Tuesday, I didn't actually go in until the next Thursday. So it was 9 days rather than 7 days. But you can see 15 minutes cure, 2 hours cure, and 9-day cure. It makes virtually no difference. The silver coated paint is effectively ready to use, and gives a reasonable performance almost as soon as the minimum curing time is allowed. So what about repeatability? Well, again, here we see the result of 2 connections of the same shield. Make the measurement, flick the thing off with your finger, literally, comes off that easily, clean everything up with some solvent, and then reconnect it. And again, we get a very, very similar result. There are some minor differences, particularly at the higher frequency. They may, in fact, be due to small position errors between the installation. Again, the experiments perhaps could have been slightly better controlled, but we think that might well be the issue. So there we are. There's our work on looking at board level shields. So where are we? Well, we can say the board level shields are different to other shielding structures because of their size and construction. Rather complex external environment, typical installation, means that a simple measure of shielding effectiveness is perhaps not appropriate, and a statistical approach that we've been looking at for the last several years offers perhaps better information. And this fragility of the board level shield structure means that if you're going to solder them on and off, it's not a good idea for reuse of both the jig or the shield. And that silver conducting paint seems to offer a reliable solution to this problem. So those are the sort of principal solutions, if you like, or principal conclusions from this sort of installation bit of the talk. What didn't I talk about? Well, in the picture I showed you, I pointed out the structure of that shield on the jig there, and you can see that the sort of the fine structure of the board level shield makes it somewhat variable. And we've been fortunate with the project of getting from some of the manufacturers some data, some modeling data that we can put into CST and actually model these things. And John Dawson has been doing some modeling of these board level shields. I haven't included any modeling in this presentation. I'm merely on the hour as it is. We have a paper in the EMC Europe coming up in Gothenburg in September. And if any of you are going to look at either go to the conference possibly, or look at the conference proceedings, you'll be able to see that paper. It'll be an IEEE Explore after the conference as well. And we can look at some of the modeling results, which are really quite good. But it does show on the modeling, you can vary those gaps in the board level shield in the model. And that gives you some idea of how the variability of those gaps affects the shielding effectiveness. And it does have a significant effect on the shielding effectiveness of those shields. But that's for another paper in another presentation. The other thing that we've been looking at is really what shielding effectiveness is all about. We've been starting with our notion that we really ought to be looking at the contents of a shield. when we're talking about the shielding effectiveness. We've been looking at absorption cross-sections of contents in board level shields. In other words, for a given energy density incident upon them, how much energy is absorbed. And of course, the ratio between energy density in watts per square meter and what's absorbed is an absorption cross-section in square meters. And so typically in a shield with apertures, ventilation apertures and so on, what you've got is transmission cross-sections, which enable energy to get in and out of the shield, and absorption cross-sections of the contents of that shield. And that is perhaps a better way to look at shielding effectiveness in the longer term. It's the actual physics of what's happening if we make our shields out of metallic conductors that have effectively infinite planar shielding effectiveness. In other words, all the energy getting in and out of the shield gets in and out of the apertures. It doesn't actually go through the shield material. But that's for another talk. So there we are. That's really all I have to say. I'm sort of 55 minutes in. So does anybody have any questions? The any questions slide has got a picture of one of my favorite places. And this is a 5,000-year-old Neolithic stone circle, Castlereagh stone circle in northwest England, up in the mountains there, where my wife and I love to go and walk. So there you are. I'm going to stop my share there and see if anybody has any questions or comments.
Okay, thank you so much, Andy, for your presentation. Very good. Let's take some questions now. There was one question in the chat. So let's see, that was from, what's it here? Joanna. Joanna, you want to go ahead with yours?
The question is, in any of these metal boxes that you're using for testing, particularly the stirred chamber, are you doing anything to control the Q of those resonant cavities?
Yeah, well, if you recall back to the small enclosure that we used with the apertures and the polyurethane foam, carbon-loaded foam, we were looking at sort of with and without the foam, with and without the apertures, controlling the Q of that as an equipment enclosure. We didn't control the Q of the reverberation chamber. We used a reverberation chamber in its sort of native sense, if you like, and it's got a Q factor that goes from a very wide range, actually, as we go up to 20 gigahertz, up to sort of several tens of thousands. The idea of the reverberation chamber there, I say, was to mimic lots of external environments. So that is something that we really do need to progress in many ways, to look at whether we should be controlling the Q of the measurement environment of the board level shield. As I say, this is quite early stage, if you like, but what we think we have shown is that the real environments, or the mimicked real environments, using the different real enclosures there with the board level shield inside, what we actually measure in those is contained within the variability we get from the reverberation chamber measurements. Did that answer your question adequately? Hello?
Joanna, was that a good answer for you? Do you have any more questions?
Now that covers it.
Yeah, okay. I hope so anyway, yeah. Early days. But you're right, Joanna. I mean, we do need to think more about the Q of the measurement environment.
Okay, the next question's from Dan Beaker. Dan, go ahead with your question.
I'm just, basically you're talking about the shield absorbing the radiated energy, but it's really not doing that. It's just forming a boundary. I mean, with the field, either it's converted into kinetic energy by reaction with molecules of some dielectric or some material, or it's contained within a space. So you're not absorbing it as much as just keeping it from going anywhere.
I think you misunderstood. Sorry, I think you misunderstood what I said there. The absorption I'm saying is in the contents of the shielded enclosure. So inside the shielded enclosure, you've got integrated circuits, you've got...
Right, I understand.
That's where the energy is going to be absorbed. And
no,
The
It's
shield-
just going to be contained.
No, hang on. No, you absorb energy in the contents of the shielded enclosure. Believe me, you do.
No, you don't.
No, you don't. You keep it from going anywhere else. You're forming an enclosure that forms a boundary just like a ground plane would do. So you're extending the
fine.
ground plane so that the energy that's being created by the switching events by the ICs is going to stay within that space bounded by the enclosure.
Yeah, but the shield.
But it's not being absorbed. It doesn't disappear. It's just
No.
being kept from expanding. So it doesn't radiate. It stays within the board topology.
Yeah, I'm sorry. I'm going to disagree with you there because we've done lots of measurements on this. You do get absorption into the contents in the enclosure. We've measured circuit cards in enclosures.
Well,
And
no,
you
it keeps it from radiating. So the radiated emissions are going to be significantly reduced,
Yeah, hang
but
on.
it's not disappearing.
No, what we're getting with the shielded enclosure, doesn't matter if it's a board level shield or any other shield enclosure, is that the energy, let's talk about radiated emissions. The energy emitted by the contents of that enclosure, the circuits within it, will be partly absorbed by other contents within the enclosure. That's going to happen. And some of it will escape from the enclosure through apertures,
But the
penetrations and so
absorption
on.
is very, very little of that energy is going to be converted into kinetic energy because that's the only way it can be absorbed, or else
It's
it's
the
stored in
arctan of the PCB.
I mean, maybe the words are wrong, but you can't, it's a matter of keeping it from going where you don't want it,
Yeah, I
not
know.
from
This is basic
absorbing it.
shielding.
It doesn't go away.
Yeah, okay. I mean, look, this is just basic shielding. The shield is not perfect. It's got apertures.
Well, I understand. And a shield just forms a boundary so that you have a waveguide that in this case, which is better than what's on the circuit board, which is a two-sided waveguide. Now you're creating something that's not quite a complete enclosure because there are apertures, but it does limit the energy escaping from that space to whatever is resonant with the frequencies of the apertures.
Yeah, and I don't think there's any
I
argument
think
about
what
that.
you've shown is an extremely effective way of measuring the effectiveness of it, but maybe the way you're talking about it's a little bit misleading. There
I
are
hope
materials
not.
you can buy that do absorb the energy.
Yeah.
There are a number
Well,
of materials you can buy that will interact with the electromagnetic field and basically convert it into heat. And
Sure.
there's all kinds of stuff you can throw on the bottoms of a PC board or whatever you want to do.
Yeah,
But
well, people
the
hang
whole
on,
purpose
Dan.
of shielding, because Ralph Morrison's my mentor, so I'm really focused on, managing fields, and the metal is what you use because you can't go through metal. So it keeps it in its place.
Okay, let's think about that for a moment. Sure. Let's assume that we've got a perfect electrical conductor to make the shield. It's not perfect, but let's assume it's perfect. Then fine. The shield will form that barrier and will, as you say, will have some containment function. The only energy escape can then be through apertures, and the apertures will act as little dipoles, equivalent dipoles, and you will get some escape of energy. But within the enclosure, if you look at the circuitry within the enclosure, that circuitry will absorb. Let's imagine you've got an emitter inside the enclosure that's you need to put a shield around. You contain the energy from that emitter within the enclosure, or largely contain it within this by the shielding effectiveness, which is not perfect, but you largely contain it. But some of that energy will be absorbed into other components within the enclosure. They're there. That
Some
energy
will be redirected into the transmission lines on the board,
Yeah, yeah.
and some of it will be absorbed in the fact that it'll interact with the plastic in the packages, and some of it will be converted into heat interacting with the dielectric of the circuit board. But that's very small amounts of that energy. Mostly what you're doing is keeping it from going anywhere, and it stays inside the circuit board.
Sure. But if you
But
look
it
at
doesn't, it's still there. It doesn't disappear.
No,
Absorbing
it doesn't
it goes
disappear.
away.
I mean, it can't disappear because that's conservation of energy.
Well, it's either converted into kinetic energy or it's transmitted somewhere or it's stored
Yeah.
somewhere, because that's all you can do with field is three things.
And that's, I don't think we've got any argument about that, but I think if you look at what happens inside a shielded enclosure, you've got a number of processes going on. You've got transmission through the enclosure boundary, let's call it that, through the apertures and so on. Typically,
leaking.
Leakage, right? And then you've got energy absorption within the enclosure, energy generation and absorption within the enclosure.
The only thing that's going to absorb energy inside of that shield is the arc10 of the PCB. The arc10 of the metal is minuscule.
Nobody's
And so
saying
you
that the
have a
metal
force
absorbs energy.
0 at the shield, and you don't have a force 0 at the printed circuit board. You do have a force 0 at the copper shield.
I'm not saying that the shield itself, the shield material, is the significant absorber of energy. It's the other contents.
But
of the
they
enclosure.
aren't either. They aren't either.
Yeah, believe you me,
They're-
Dan, I've
You're-
measured this.
You're containing the energy is a good thing, and that's what a shield does. You know, you aren't doing anything to absorb the energy.
Well, you
There's
simply
no
got other
structure
things
to absorb the energy.
Believe you me, look, we've measured this.
Well, you're measuring how much of the energy actually escapes from the enclosure, and that's what they're for.
Yeah.
But
Well,
it
that's the
doesn't
shielding effectiveness
disappear. It just
measurement.
means it can't escape.
But that's the shielding effectiveness measurement. That's what I've been talking about.
Oh yeah, and that's good.
But believe me, that energy, if you're talking about how the enclosure actually works and what it's doing, you cannot ignore what's inside it. And I'm not talking about the walls of the enclosure, although they do have a tiny, tiny effect.
The
But-
energy just goes other places on the circuit board.
Yeah, and it goes other places on what's inside the shield.
But that's not, it just redirects it instead of radiating off the board.
Yeah.
It redirects it inside the PC board structure so that it
Sure.
can't find a radiating antenna to cause you problems with emissions or susceptibility for the parts.
Yeah, and so if you accept that energy is contained within the shield and it's absorbed by either intentional absorbers of that energy, the load at the end of the transmission line or whatever, or unintentional absorbers, other things, then you have to accept that the amount of energy getting out of that shield is determined by the structure of the shield and what's inside it.
I think it's more dependent on the fact that you're preventing it from radiating from the wire bonds and
Yeah.
lead frames of the ICs, because those are what are forming the antenna structures normally.
That's true.
It's
And,
got
those
more
are-
to do
what
with
you're
the
doing
resonant
is-
structures you're building. Those metal boxes are going to resonate at very specific frequencies. And so at any one of those frequencies where it's resonating, that box will absorb, that poor word, that box will hold energy specifically quite well at those frequencies. And so anything that's inside of the box is going to see that energy.
Yeah.
Because there's
And-
nothing to absorb it except the
And the
arc10
big
of the
thing is
PCB.
it takes the changing E field creates the H field. It takes that H field instead of having it around a wire bond, so it's a very strong localized field. It distributes across the surface of the enclosure, which reduces the magnitude of that magnetic field so that it doesn't do a whole lot to cause any disturbance in the E fields adjacent to it. Just like a ground plane, it's just wrapping the ground around it, or a coaxial cable, same thing. I mean, it's good stuff, but it's not absorbing it.
I think
Maybe it's the language we're using, because Ralph was really mean to me when and taught me the language. So
Okay, I'm gonna.
anyway, this is wonderful. I appreciate it.
Okay.
Not
I'll
trying to be
jump in
mean.
here. Sounds like we're going in circles at this point. So, so we don't lose everybody. We've already lost a couple. I'd like to see if there's any additional questions, and then we can move on to the drawing. If you have any additional questions, open up your mic. Okay, I'll throw a question at you. Did you consider using you know, like a shield, removable shield, like, you know, like a shielded enclosure door where you have the finger stock, you know, and the socket. Did you consider something like this, like you could just, you know, pop on and off if you wanted to remove the shield and put it back on? Did you consider anything like this?
What, for the board level shields?
Yeah, for the board
Yeah,
level.
I mean, we didn't consider that. I mean, such a structure would be actually very, very small to
Yeah, yeah.
fabricate.
I think there is such a thing you can buy. I think there is something in the market.
Maybe,
something
yeah.
like this. Anyway, if I run
We
across
didn't
it,
know, but
I'll send you that.
The normal application of a board level shield is by soldering.
Yeah,
as you can
okay.
see.
I think there,
And so
And
we,
those mechanical connections are pretty fragile. You put 3 or
Yeah.
4 insertions on it and they're not as effective anymore.
yeah, I understand.
Or braid. I mean, you know, there's
Yeah.
some of those structures, but I think the metallic paint was a great solution.
Yeah.
Pretty
I like
ingenious.
that. Yeah.
yeah, I mean, that's very simple to apply as well. I'd say, I mean, you want to get rid of the shield off the thing, you just click and it's gone.
Very
In fact,
good.
when we
I
started
wouldn't want to
doing
be
it,
the one doing the vibration test.
No.
Yeah,
In
okay,
automotive,
we'll
it
do
has
it.
some issues.
Yeah.
This is just for empirical lab work. So
Sure. Any more questions? Okay, let's move on to the
Would you like
drawing.
the equation for the resonance structure that metal enclosure is?
The Helmholtz equation, yeah.
Here's one, if you will allow me to share it.
Oh, okay, give me a second. Where are you on the screen? Oh, there you are.
See if I can find
Okay,
it.
try it.
Well, I guess I can do the entire screen. I'm having a problem with finding Keynote. Come on, share. I don't know if you're seeing it or not, though.
No, we do not.
I got a permission problem.
You are a co-host, so you can share.
Yeah, on my side.
Yeah, should you go to the bottom center there was a share screen and pick which screen it's on?
No, on my computer, I have not allowed sharing.
Oh, I gotcha. It's a security issue on your end. Gotcha.
as the host has disabled sharing.
No, I enabled it for Joanna.
Okay, mine it says I'm blocked.
Everybody else is blocked.
How about that? Do you see it now?
No.
Phooey. I'm telling it to share,
You have too much
but
security.
it's not coming through. I think it's a security problem.
Yeah. All right. Well, I'll
Oh,
work
well.
on the
Next
drawing,
time.
and then we can circle back to that afterwards. Or we're done with the drawing. People can hang out here if they like. So I use a random number generator from random.org, and I put in the random numbers 1 to 100, even though we don't have 100 people here. The first random number is 61. And that person is not here, at least that I know of. Ravi Ranjan. This is for $25 gift certificate. Next one was 74. Matt Tao, he's not here. At least, Matt, are you here? Some of these people might have signed in late. Third number was 36, which is Mike Kirkhart. Mike, are you here? No. Weather's too good.
Yes, I am. Yes, I
Oh, there you are. Okay, Mike.
Yep.
Mike, you just won $25 Amazon card, and I'll be sending, you'll be getting
Cool.
that.
I can buy more books. Woohoo.
That'll be going to mkirkhar@umich.edu.
Yep, that's correct.
Okay. Next one is number 38, which is Arun Kumar. Arun, are you here? Next random number was 13. This is for $50. 13, Chris DeWitt. I don't think he's here. Next one was 73. Ya Qing Tang. Ya Qing, are you here?
Yes, I'm here.
Excellent.
Nice. Thank you.
So that'll go out to ytang2@ford.com.
That's correct.
$50 Amazon. Watch your email. Watch your junk mail. I'll be doing this in the next few days.
Okay.
All right.
Thank you.
Congratulations.
Thank you.
Next one's number 46. This is for $50. 46. Marlon Badra. I don't think that person is here. Number 11 is next. Ben Carroll. Ben, you still here? I saw you on earlier. Ben Carroll. For $75. Going once, going twice. Gone. Next one is 25. Bruce Hanson. Bruce, you still here? Bruce Hanson, unmute if you're here. Bruce Hanson, going once, going twice. Gone. 68. George Siama. George Siama. George, are you here? I don't think so. 16. David Evans. David, you still here? No. 19 is Akio Fujimaki. Akio, are you here?
He's
I'm
around.
here.
You won $75 gift certificate. Congratulations.
Thank you.
You're welcome. Okay. Well, thanks everybody for stopping by our Zoom meeting this evening. Again, next month is going to be our picnic. We haven't really done a picnic before, so this is something new. We're looking at a few different things. We've looked at barbecue, we've looked at Chicken Shack, and we're currently looking at actually an Italian restaurant. So might that be pretty good. So keep your eyes open for that. Again, it'll be limited to our seating there. So at this time, I'm going to stop the recording, and then you guys can stay on here and chit chat to your heart's delight. So anything else before I drop off here? I'm
Scott?
stopping the recording. Go ahead, Akio.
Information about the picnic, is that will be at our website?
We're still working on it. It's not released yet. Yeah. It'll be you'll be getting an email. Everyone will get an email when it's solidified. We're still working out the details. Okay.